Uh, okay. So we'll try to cover DDPM paper today. So that's Denoising Diffusion Probabilistic Models. And this is currently what's like the foundational idea that backs stable diffusion or diffusion LLM, like anything, any model out there with that name diffusion. Yeah, this is where it mostly starts. And this is not the original paper, however, that actually coined the idea. That was a different paper that was from 2015. And if I remember right, let me see. Attention is all you need. Yeah, it was this one. It's deep unsupervised learning using non-equilibrium thermodynamics. It has a very fancy name to start with, but it has nothing to do with thermodynamics. Like it draws some ideas, but it doesn't do much with it. So I won't go in this direction because I've done this throughout the morning and it didn't help actually. Because like again, as I said, like it draws some ideas, but it doesn't implement any of that. So what I'll do is that I'll actually go through some basic intuition to explain like why does DD like why diffusion, like why should we do diffusion, why not the alternative, what's wrong with the alternative to start with, right? So we'll start with that and then go with like covering like what the 2020 paper actually ends up doing in the end, right? And then we can like start taking questions and all. Okay. uh, yeah, so I have a image here which basically kind of outlines a set of things that are happening in the generative modeling space or have happened historically. I'm not well versed with the flow based models though, to be very honest, but GANs and VAEs is something that I work with, so I can quote about those. Um, Now, about GANs and VAs, I'll give a basic history on their approach, like how did they happen to be it. So basically there's something called as Boltzmann machines, and then based on top of it, like people try to actually do various different kinds of ways of generating images or generating any kind of data distributions. So the end objective is that you want to learn a distribution, right? And GANs and VAs have two different approaches of how it wants to really go about it. GANs like particularly focuses on basically having a prior from some normal distribution. Sorry, wait a minute. Yeah, like having a prior from some normal distribution where you have like, I think I'm not able to write on it. Wow. Yeah. Yeah. So this is generally a normal distribution that you sample out from, which variance of one, mean of zero, and then this is an image which belongs to your own domain, and the discriminator is responsible for actually identifying whether the generator is able to learn the domain itself or not. So basically you train your discriminator once, you go back and then lock in the discriminator, you do a forward inference on the generator and then do a backward pass, like the discriminator is kind of sitting here, and then do a backward pass to basically train the entire generator. You keep doing this again and again for like various different samples of z that you can draw out, and eventually you expect, okay, the generator will learn something, right? Like it will learn the distribution. VAE has a very similar approach, the only difference in being that how it actually sets up the problem. VAE actually focuses on learning the mu, that is the mean and the variance of your data set, and then allows you to, during inference, just pick up any z and then do an inference through the decoder, and you will get an image. During the training, we actually have a KL divergence loss on top of mu and sigma against a Gaussian, because I want Z to be a Gaussian to start with. And my decoder, like, sorry, and finally a reconstruction loss between them. GANs can also have reconstruction loss if you are feeling fancy at any point in time. Like there were variations of it, but it's not exactly in the original paper. So this is the setup for like GANs and VAs. I don't know about the flow models much, so can't comment. But one thing that you might have noticed in both of these approaches is that you have some, sorry, you have some noise Z. right? And you ideally want to sample it from some Gaussian, right? Let's just like give it mu and sigma, right? Okay. Right. Mu and sigma. And you want to learn a function that can take this fz and convert this into an image domain, right? Like which roughly translates to basically your f is trying to learn x of image given some prior. You will keep encountering this name all the this word all the time. Prior generally means this one. Like this is your prior, like your noise, or based on which you want to generate, and this is what you want to. This is what you get. Like, this is what you generate. Your function learns this, right? But in practice, when you actually like work with it, you basically end up with something like this. This is your like your learning objective is dependent on this one, but your actual function, like as in the network, when you actually do an inference, will end up doing this. Your z is whatever value you want to put in. Ideally, like based on VAE and GAN's formulation, it's this one. Now, the, it's not, I won't say it's a problem, but at least in today's date, GANs have kind of faded out, and maybe rightfully so, because, and that's what like diffusion process highlights in their paper. Diffusion actually came just around, I think, 2015, and the original GAN paper by Goodfellow was around 2014. So these work were done very close to each other. What you will see here is that you are trying to learn a noise, like a mapping from a noise to a more structured data. Let's call it like wait, let's call it I, right? In a single step, right? So that means whatever model you have which does this transformation must have the capacity to do this kind of inference to start with, which may or may not be a lot to expect if you think about it, right? So because there are a lot of noises that can actually map to an image, right? So like you might have a noise sample like 0.00001, another one might be 0.5, and maybe they might get actually mapped to the same image, right? Or it can it won't be the opposite of it, but this is definitely true. So in such cases, if your model does not learns the probability distribution function properly, then it cannot give you a good output for this value. Maybe it might be able to learn for this, but this not this. Think back to autoencoders. If you have an input image, right, and you train a model like this, right, and you basically compute this loss Frobenius norm. Basically, this is your loss, right? So this is your autoencoder setup. In this one, why this cannot work for generation is that is this the same thing, right? Like your image will have some value of maybe I1, right? And for it will have an encoding, right? Encoding of suppose E1. And then it tries to actually estimate the I1, I dash 1, right? Suppose there are several such kind of encodings till En in the domain of suppose E, right? There is, we know there is, but that doesn't mean you have trained your model with every image which covers the domain. So effectively, an autoencoder ends up learning a very good hash map. So if your distribution would have looked actually something like this, maybe because of your limited samples or and your training methodology, you might just end up learning a very small subsection of your distribution. And what happens when you actually give a sample around here, which is something like E, A, or EZ, somewhere in between, your model doesn't knows it. Whatever the curve the model has actually learned, that part does not covers this one. So it cannot output a usable image. Another way to actually think and look about it is that, like, what is this loss actually trying to do? You are actually trying to This is like, okay, sorry. Let's just write the proper form of it. Although I'm writing it as a square, but you have an expectation term here, right? You minimize the expectation of it, which means you're basically averaging all the images, right? When you actually try and learn this based on this loss function, you actually are learning an average of all the images. So at any point in time, even if you actually give some EA value, you maybe it is a good function. Let's assume it's a good function. Even in that case, what's going to happen is that a lot of such values like EA1, EA2, all of them are going to collapse to the same image, which means EA should have corresponded to just dogs and EB should have corresponded to only cats, but you end up collapsing the images altogether. Like, and then you get an average of some, like, you have a dog and then you have a cat altogether, and it's a mismatch of all of it. And it's not useful to start with, right? You want at least some determinism. Like if I give a Gaussian value range from some 0 to 0.5, then it should give me cat. Or if from 0.1 to 0.2, it should give me a dog, right? Because otherwise your priors are not fixed and you cannot work with it to start with. Right? You're going to get a mismatch of all different classes that you have. So that's the problem with GANs. Sorry, that's the problem with autoencoders. And that's also a problem with GANs if you don't train them properly. So there is also an added problem of instability, right? So there are like all of these issues that are present there only and only because we are trying to learn we are trying to learn this mapping function directly. Like you are jumping from the prior noise to the final image in one shot, and we don't know the model has enough capacity for that or not. So that's where come in the diffusion paper suggestion is that let's not go ahead and learn it at once. Let's do it step by step, and that's where like this famous image also comes from, right? I'll pause for a moment. So far, any questions, anything folks want to ask? uh,
Uh, Sorry if I misunderstood something. But then when you spoke about Z, you said it's a normal distribution with mu and sigma,
Mm.
right? But what if the noise
Yes.
is not following a normal distribution?
Sorry.
What if it's not following a normal distribution? Like, it could be possible that there's some kind of noise that follows some other distribution or does not follow any distribution.
Wait, let me go back here. Where you're pointing out, because when I say like there is a mu and sigma, it's generally actually 0 and 1 only in most of the VAE setups. But if you want, you can actually set it up as something else. But that just makes your overall equation more difficult to reparameterize. But like, yeah, honestly, I didn't get the question actually.
Isn't Z the noise?
Yes, Z isn't okay. Um, So if you are in the regime of GANs and VAE, Z is not a noise. It's the latent vector.
Okay.
Yeah, that's the word they use, like what everybody uses. And you might also hear the word again if you like work with latent diffusions. I was just reading through that, and they basically do the diffusion process in latent zone. By latent, it just means that it's not in the original domain that you're working with. So if your original domain was with like realistic images, you actually convert it into some known distribution,
Okay.
right? So the embedding values. So if your embedding size is like 32, right? Yeah. So
Which is why you know that it will follow the distribution because you're generating.
yes, yes, exactly. So like it doesn't matter what kind of images you like, dog, cats, or like shove in whatever you want, but you know that your embedding that is going to learn that will always be in like a mu of 0 and 1, and it's of size 32. So now for you, you can just sample a random z, and then like your decoder can handle this in that case. So yeah, that's exactly the reason why you do it.
Okay.
Yeah.
But for
Now,
diffusion, you won't generate the input, right? You'll just take some input in the wild and feed it to your model.
can I repeat the last one?
No, for diffusion, like you won't constrain the input, right? You can give whatever input you want. So how will Z always be a distribution of mean zero and like deviation one?
Oh, wait. In diffusion, we do end up adding that constant. Again, it's just for like ease of doing, like setting up the training overall. So if you see here, like I will just, yeah, this one, right? So this epsilon, wait, can I improvement? Yeah. So this epsilon that you see, that's again like coming from a nu of 0 and 1, because it's just easier to sample in that way. That's it.
Okay, makes sense.
Yeah. Yeah. Uh,
So I have that question. So I'll just summarize it. So basically, what you're saying is that V and GANs, the joint probability that they model is sensitive to the input uh, because it is sensitive to the data we are seeing. And well, we have not come to diffusion, but it seems like diffusion avoids the use of using an encoder and does it directly on the noise itself. So you don't need this latent variable part of it. I'm getting that right.
Again, you missed on one point. So what I was like at the very end, I did made this concluded one note here that we are trying in all the approaches that I discussed, all these latent variable approaches that I was discussing. In those, we were actually trying to learn the mapping from the latent variable directly to the image.
Right.
Now, if you consider the latent to be a noise, right, because it is a noise, you are actually just sampling some value, you can like call it a noise. So that no,
Mhm.
you're trying to learn that mapping directly. However, like the diffusion paper says that you cannot do it. It's an intractable problem.
Okay.
It's simply not possible to learn that. Like basically, in order to do that, you will have to like estimate the marginal of every single image to ever exist. So I think I have clearly
Uh,
noted this one. Yeah, so, yeah. I think this is how it roughly kind of looks like. They're trying to get an image from a noise, but like if you go by the Bayesian, the setup somewhat looks like this: that you have a noise, then you have an image, and these are like particular image values. So this is like a noise value. This is a particular image value. Then the probability of an image value, you need that, which in itself can be a marginal,
right.
and then you have this one, the marginal of the noise itself, for all the images that there can be, which is downright impossible to calculate. So every single variational autoencoder or GAN variations are trying to solve this,
Mhm.
expecting that the approach can solve it.
Right.
Diffusions, yeah, the authors of diffusion says that you cannot. So
Because
we are going to take it.
there's a lot of random variables and a lot of images in game. So
Exactly, it's just simply interactable. It's on a continuous
mm,
plane. There are infinitesimal number of values. So we're going to go in a different way, which makes the problem a little bit tractable.
fair,
Right,
good.
so that, yeah, so that's where the entire motivation of like diffusion comes into picture, because everything is trying to solve this, and we know it cannot be solved. Just because like you're throwing the model doesn't mean it will solve it. That's the claim though. But GANs, like historically, if anybody have followed style GAN, they did pretty well. Like I mean, style GAN had good output in general. uh okay, next goes is like what diffusion does then, right? So if I, so diffusion again, like I think best to show it from the image, from the paper itself. So diffusion again follows this uh, route, and I think everybody already knows this, that okay, you have a image here, and then we kind of start adding some noise, then you add a noise again, and you keep going it until like you have the actual image back. And this is actually the reverse process. Like let me actually erase it so that it's more easier. Mhm. Yeah, so this is actually the reverse process that's being shown. The forward process is more like that: you have an image, then you add a noise here, then you get this one, and then you again add a noise here, then you get this one, and you keep going like sum for t steps. If you do the reverse, like if you are able to learn the reverse function, then you can actually have this image as well. Like you might have already seen this, but yeah, roughly speaking, that's what actually diffusion says. So this is the original equation, and you might keep seeing it again and again in all of the like blogs or papers that you were wherever you read, this was the original 2015 equation, papers equation. Like you can see, this is the forward trajectory. Forward trajectory, as in I start with some image and then I keep applying noise on top of it, right? As I keep applying a noise, at some point, like, okay, I will stop and then I'll have a completely noisy image. This is the forward trajectory, right? And this is the backward one. Basically, once I have the noisy image, which is this one, I can then again reverse this entire process, right? You can see this one. I can reverse this entire process to go back and get my original image, right? So that's what diffusion says. Diffusion says that, okay, you don't have to learn a function which directly translates from the noisy vectors or the latent variables, a function which maps that to directly the image domain or the domain that we are concerned about. You don't have to do that. What you can do, and this is again like that's where the intuition of this thermodynamics and physics comes into picture, is that for any stochastic process, like if a system is in like a state z of distribution and it goes to state x maybe, so you cannot just like there is no single mapping which makes it from go to x to z. It's always a process where the distribution slowly changes, and that's where the whole idea of diffusion comes in. Like there will be a lot of examples if you ever actually end up going through some blogs which gives hand wavy explanations. They'll say that it's like similar to how an ink drop, if you actually put it in a water, it's not going to suddenly diffuse and get uniformly distributed. All the molecules will not do that. So it's like that. You can think of it like this, but I don't find it easy to think of it like this because again I don't have a physics background. For me it's more easier to understand that, okay, I cannot drag one distribution to another distribution just in a single shot. It's just more easier to add noise bit by bit to the prior distribution that I have. Prior as in like whether it's a noise or it's an image, whatever be it, I can add some noise, some extra salt on top of it bit by bit to actually finally transform it into the distribution that I want it to be. And that's the crux of diffusion paper. And this is how, like mathematically, this is how it looks like. This is how it can be expressed. So this is your like this is forward diffusion. Forward diffusion looks like this, and this is your backward. Just for notation purpose, whenever you're reading the papers, it's just easy to remember that if it is written as q, it's the forward function. That is, it's trying to learn from image to noise. And now we can noisy image. Actually, noisy image would be a better word. Yeah. Now we can use the word noise because in the original DBM paper and as well as the later 2021, they actually use the word noisy image, or the noisy afterwards that comes from the prior. Posterior that comes from the prior. Uh, P is the backward function. Backward is where you actually go from noisy image back to the actual original image. So again, that doesn't happen in one single shot. You actually take noisy image and then make it less noisy image, right? There is some like explanation of like how we actually make this problem tractable, because again, coming back to it, this in itself is also not tractable. So there's a lot of math here. Like we can probably go it afterwards. Like I don't have a full great understanding as well. So yeah, I'll probably skip this because I've been studying it, and yeah, I think it will probably waste a lot of time. I will share this note for anyone so that they can actually catch up with everything, like all the stuff that I've read through. So it's more easier for everyone. I'm just highlighting the equations which will matter later on. So in the diffusion paper, you will again kind of encounter the original equations variation. So just a moment back, I showed that P was the reverse process. So for reverse process, you have this P theta, right, of xt minus 1 given xt, where xt is an image at some time step, and xt minus 1 is the image that was before it. That is, we're basically in this case, it's P, right? So it's basically denoising it. It's the reverse process. You need to focus on this one, like how we are actually sampling, or basically the P theta function. The P theta function is this. which is basically like your mean is taken from some mu naught based on xt. That is that basically this is a function. There's a function that learns the mean, which there should be based on some parameter theta for xt. Again, I'm just explaining the notation so that you don't get confused from the paper itself. We'll come to the actual implementation, and then this might look completely useless. So I don't know. And this is actually for the variance, and that's it. This is a reverse one. This is a forward process. This is the Q. Wait, Q is, yeah, Q is forward. Q is forward process. And in forward process, you will encounter this one where you have, okay, I didn't write it properly. Just show it from here. So you have 1 minus beta t, xt minus 1, and then beta t I. Now, the beta parameter is quite important. So I'll quickly go through all the parameters which can and will be important. So you have beta, which basically says the diffusion rate, right? So if you have some diffusion operation, right, and I'm not going to like I'll show you the equation again, but just assume that you have a diffusion equation denoted by this plus or sigma operator, right? What we need is that what is the scale of this operation to happen? Like I mean, if at beta time step of 0, maybe I'm setting the value at 0.1, 0.01, right? But then time step of 1000, I'm actually setting the beta value at maybe 1.2, right? Now, what is beta? Let's go back here and then we'll quickly see. Hmm. Wait, sorry. So I mentioned what beta was like. It was the diffusion rate. But in the paper, like while implementing, you'll encounter that we don't use beta directly. Again, it's one of those reparameterization trick that just makes like the equation much nicer, so that it's easier for us to code and then actually do the optimization of it. So we actually use alpha t, which is 1 minus beta, right? And then that gets translated into this. So the operator that I was talking about is this one. It's root of alpha x naught plus 1 minus alpha t epsilon. Epsilon is the noise at timestamp t, right? So right now we know about two parameters. One is beta, which is equivalent to which is equivalent to 1 minus alpha or the opposite of it. And then you have time steps. Time steps, just for clarification, time step means that you are going through all. So how many number of times you're adding noise and how many number of times you're actually subtracting the noise. That's what time step really means. That's it, right? So you have time steps and you have beta parameters, right? This graph that I was showing here, the x-axis is the time step and this is the beta parameter, right? This is like, again, this is a word that you will encounter. It's called beta schedule, and that schedule basically determines that whether this graph is linear, whether this graph looks like a sigmoid, whether it's a sinusoid, or how do you want it to be. Any questions so far, like before I actually go ahead and start talking about the training regime? Mm, guys, uh, hello.
We're all
Yeah,
there.
we can.
Yeah, wait, what? Sorry.
No, I said we're all there.
Yeah, I mean, like you're there, I know that. I'm just asking, like, it's like,
So,
I
so,
mean, any
so
questions?
basically, you're just removing the noise at each step, right? Using the schedule of beta.
Yes, the again, this, I'll just quickly show this one. This image should explain it. Beta is this one, 1 minus alpha t, that's beta. And that's the scheduler, like how much noise there should be. At any given time step, how much noise should I add? That's what beta determines. And if you are deciding that I want like 1,000 steps, then your beta schedule, like from x, from some value 0.02, then going up to 1.2, like how it should be distributed across, that's your beta schedule. So yeah, beta is basically, you can say that, okay, that's the scale of the noise, not the noise itself, because your noise itself is coming from this one. That is
Cool.
your
Got it.
Gaussian distribution of 0 and 1. Okay. Um, so let's go to the training regime quickly. Now, I haven't explained any of the model details, because that's up to you, right? Because there are a lot of variations of it. You can write a very simplistic unit, right? Uh, you can actually search the architecture here. I don't want to like cover that here. You can also go ahead and add like within unit you can add attention based layers as well, right? And then if you want, you can actually, so there's, I think, one diffusion transformer which only uses transformer layers, right? So the model is not of concern here. What is of concern is that what do we want to learn out of the model, right? And how we actually do the inference itself. So what do we want to learn in the end, which is the loss simple in the end, is that you have an epsilon of epsilon, which is the noise at any given time step, and then you have like wait, you have this noise applied image. So you're applying the noise on the image itself, right? Then you apply the function on it, and this is your neural network. Your neural network is now responsible for predicting what was the noise added to it, added to the sorry the added to the image, right? If I go back here, I have an image, I add a noise, I give it to the network, and the network is responsible to estimate the noise itself, like what was added to it. While we do this, and this is the current practice, is that the network itself at each layer also gets an input of which time step it is currently in. That is the value of t, the t value that we're actually using, right? So that it actually knows that, okay, which time step it's trying to denoise, not denoise, sorry, which time step it's trying to estimate the noise for this given image. So it estimates the noise, and the loss function, as we already discussed, is the Frobenius norm of the loss, the actual error and the estimated error, and you do a like gradient descent on top of it, and that's your training regiment effectively. For each image that you get, you use this equation, add the noise on top of it, you estimate the noise, and then you use the Frobenius norm to L2 loss to basically train the network. That's your training regimen. When you do the inference, you effectively do this, that you know the alpha range that you have picked up, like based on your scheduler. So all you have to now do is that basically reverse your schedule. So you can see, like, we start with the noise. There is a noise, we like it's just the like the first latent value that we get, right? And once we have that noisy value, we keep denoising it step by step. We keep denoising it. So you can see, like, we are going in reverse process from xt to xt minus 1 using this equation. As we keep doing it again and again, at some point, like after how many cycles? T cycles, because that's the number of times that we have decided to keep, like whatever the t value of t is, we get it x0. And this x0 is the generated image. And that's what, like, that's how diffusion really looks like. The forward no sorry the forward the reverse process of learning what noise was added happens during training, and during sampling we basically use that learned residuals, like whatever the residuals that we have learned, to basically remove the noise. The denoising is not done by the neural network itself, which was a very prevalent way to go about it before this paper. Before this, like before DDPM, autoencoders were very popular for denoising. And again, it, but autoencoders used, like, try to learn the mapping directly. right? This one, FZ2 image. So in that case, in autoencoder's cases, you would end up somewhere like you have an autoencoder and you have an image, you have image plus noise, right? And then it tries to estimate some like this, right? And you can then do the like the sorry, it's actually opposite. My bad. Image plus noise, yeah. Then it tries to estimate like this. So this is autoencoder setup, and this is what they were trying to do. They were like trying to denoise the image itself in one single shot. Diffusion says you don't need to. Just go ahead, add the noise, and then predict the noise itself. And once you have learned how to predict the noise, take the image. Sorry, take. Wait, my bad.
The noise.
Take any random noise. Sorry.
I said take the noise.
Yeah, take the noise. Yeah. Yeah. So wait, I'm writing noise again. My bad. Take the noise, right? And then basically you go through the like the reverse process of trying to estimate what was the noise added, right? So this is n, and then it gives me n lambda, right? This is actually n plus I. I just don't know what the I is. I have no idea. So now because I get the n hyphen, now I can like do this process of n plus I minus n hyphen, which is the reverse process, right? Do it again, and then in the new one I have this n minus n hyphen plus I, and I can pass it through the network again and again up till t number of times until the point I finally get my original I, that is the original image.
So,
So yeah,
so in the
that's diffusion actually.
training we have two steps. We train to add the noise, and we train another model to predict what sort of noise was added.
No, we
And
train only one model. There is only one model that we train.
okay, so we only
So
train the part where we predict what noise is added to the image, right?
exactly. Exactly. So in the original paper, it always talks about that. Okay, there is a forward process trying to learn. Okay, what was the basically you keep adding noise, and then you get bunch of functions, like not bunch of functions,
Right.
one function that tries to keep adding the noise, right? And then it also
Right.
talks about the reverse diffusion process as well. In DDPM formulation, that's in 2021, they say we don't want to learn that because we know that the beta, that this beta is constant. We are aware of the distribution. We don't need to learn a noise function which keeps adding noise. So if I don't need to learn the noise function, now I just need to learn how to go back, right? And now if you actually think about a little bit of the setup here, going back to that original idea, right? That at any point in time, if I give you a noisy latent vector, then that noise could have like, wait, what? Well, इसका ink कैसे खत्म हो सकता है?
I
Wait,
think
it's not
Maybe
working.
the battery died.
battery got on.
No, it's pretty much on. It's just see, it's working.
Like,
Jesus fuck. like इसका कैसे ink खत्म हो सकता है भाई? Yeah, that probably the app is about. Anyway, yeah. So going back to the original idea that you have some noise and then you're trying to learn the image itself and right, and you try to get some function which do that. That was VAE and GANs. In diffusion, if you think about it, at every step, right, depending upon which noise you have end up picking in, right, you actually get a lot of different options of intermediate noisy images or intermediate noisy priors. You get a lot of options and you kind of like go through all of these noisy options to actually finally emerge and come to maybe one image. However, they could have been generated from many different other images. Like a lot of different images could have end up with the same latent prior, which if you remember I was talking about, like if you have like some 0.0.5 and like 0.0.1, and they get kind of matched with the same image, right? Which was happening in autoencoder cases. It could have happened there. But in this case, you kind of reverse the problem that, yeah, fine. That like, I mean, now I'm saying this is my noise and this is my image. So I can actually now have multiple images being kind of mapped to the same noise, maybe. Like same noise, starting noise. I don't mean like the actual entire trace, because the entire trace would be different for each different images. But like
Yeah,
from where you start can be same.
I have the same question because, like, if I have to generate a specific image, how do I know which noise to start with to denoise,
Ah,
basically?
yes. That, however, is not covered by DDPM actually. So DDPM doesn't actually concerns with that specifically. Uh, for that, again, you need to like know what kind of like your priors have to be grounded to something, and I think that's where most of the work around like everything that came after DDPM. Wait, let me show you. I should have them. Hmm. Wait. Yeah, like for example, Uclip. So this architecture should give you some idea what's happening. So you have your like a text encoder, which again getting trained as a clip model on the side, while as well as the same noise that a text encoder is giving, you are using it to decode it into an image as well. Which means you got good prior, and that good prior gets decoded into the same image, or at least you try to denoise it into the same image, or denoise it into like the closest noisy image there can be. So in order, so like to answer you, like this is like how we control the prior in diffusion. And
So
one point here.
this is a control signal, let's say.
Yes, this is the control signal. Now, one point here, I haven't actually fully went into like the entire history of diffusion. There should be some control diffusion, but I remember reading it somewhere that diffusion model in itself don't have conditional class control. So there used to be something called a class GAN or class aware GAN, where basically you could pass the like an entire one hot encoded vector. Saying it one hot encoded would be wrong. It would look like an array of 1001 like that, which would actually indicate to the feature which you want to control. So maybe the one at 0th position will indicate the color of hair. The one at position 10 would indicate the size of lips, like that. And those had much better control. And that late and that this control vector you would actually kind of concatenate with the latent variable, and then you do the decoding as well. So to answer you, like GANs used to do it better. With diffusion, you get that ability to vibe code the entire image, which I don't like. If you want, like, people prefer text as an input. It's just easier. Yeah, let me see if there is mm, class aware. There should be. Is there something class? Classifier free guide. Classify guided diffusion. Classify guided diffusion is present. Okay, yeah. So I was thinking I just can explain. So I'll share the PDF for like whatever written. So there is a link for this one as well. I'll just share the link for this one as well. So yeah, you can actually take a look. So there is like, to answer you, there is a classify guided diffusion, and the classify guided diffusion, I guess, is somewhere around this. Let's take a look into how it does it actually. The diffusion sampling given a diffusion blah blah blah. Diffusion sample from U plus S. Yes. Yeah, I'll probably have to read more into it. I don't think I'll be able to understand in one shot, but it exists. Yeah, to answer you.
Yeah, I think looking at the pseudo algorithm, it seems like they're just controlling how much noise is added and then it's clear.
Yeah, it's the effectively it's the same method. The question is just that I was trying to figure out like how the noise is getting grounded to a class, and that's the
Right.
important bit. Yeah, yeah. I guess that should cover it. Uh, any other questions, guys?
When we
Wow,
say
it
we
is different.
generate all, yeah, when we say we generate all these intermediate noisy images, are they useful? Like, can we use them for something like intermediate state representations in CNN?
Intermediate state representation. What do you mean by intermediate state representation there, actually?
Like in CNN, we have the last linear layer, which say classify stuff. But before that, we have intermediate layers which maybe identify edges
Hmm.
or like. So when we say we have intermediate images in this, like say x0, x1, x2, are they
Yeah.
useful or are they things that we won't understand?
That is a good point. So, like, here's the thing. It is not useful in the original formulation, right? It's not useful in that one. But if you think from a perspective that, okay, if you try and take and ground the individual noise into something more useful, you might be able to get something out of it. I don't know. Again, I'll have to, like, we'll probably have to see if there's somebody trying that. Because if you remember resonance, right? Resonance, like, what's the architecture? You have an input, you take it, and then you add it here, right? So this effectively tries to model the residual, right? Which is like f of x minus x,
Mm-hmm.
right? So that's resonate. So you're trying to model the residual. The same thing we're doing in our case as well. So even if you're using, so you said that, okay, the intermediate values in CNNs depends which architecture you're using. If you're using a resnet, then your intermediate outputs after like couple CNN blocks are actually just residuals, and those residuals might not be that useful, because even if you visualize it, you are actually just visualizing a difference value, fx minus x, right? In
Mm-hmm.
this case, you're also going to actually observe the same. The question is, are they useful? I don't think so. I mean, like, at least in the original formulation, they're definitely not useful. But if you try and ground them into something, then maybe. Also, if you think about theoretically, right? If you start from some noise, you keep going through the diffusion process again and again, you go and like, you land onto some image, some valid image. But then again, this image is also a noisy image, actually. I mean, just because you have denoised it, nothing
Mm.
stops you from considering it a noise. Go and do the diffusion process again. Now see what you end up with. This is your image too. So maybe you can actually see it from that perspective. Like, I don't know, like, what this will result into. Again, that depends on like how your entire training regimen was. If your priors, that is where you started from, were themselves images, right? So for example, if you start from images of cats, and then that was your prior, and then your posterior was a dog, and then you train like similarly, like, okay, let's have the same model try to predict from dog to cats as well. That is, your same model is learning both. Then in that case, if you keep doing the diffusion process, it will go from dog to cat again. Hmm.
Yeah, so this is cat dog, cat dog, cat dog.
Yeah, I mean, like, in your like this by model distribution learned function, this is what will keep happening,
Mm.
which is interesting. Yeah. Yeah. Okay. Yeah. Anyone else? Any other questions? I have a feeling today's was quite heavy. Like, I'm not sure how good of a job I did. Uh, yeah. Uh, if there are no questions, maybe we can pause. Uh,
Sure.